Hello. So, in today's lecture, we will discuss another chapter, another section of quantum mechanics, and which is a very important and at the same time very interesting topic, very interesting situation when we are studying the Schrodinger equation and the solution of time-independent Schrodinger equation in the different potential situations. This potential is of a particular interest in theoretical physics. In many situations, we come across this mathematical concept, and it is called the Dirac delta potential. So, before starting this Dirac delta potential and what is the physics behind the Dirac delta potential, we will start with some preliminaries from some preliminary concepts that I have discussed in the last lecture videos. But let me remind you in a short time that we have at our disposal two types of wave functions. One is the normalizable wave function, another is the non-normalizable. The normalizable wave functions, they are generally found in the case of a particle which is moving in a restricted region of space or within some boundary, you can say, so that they lead to quantized energy which is specified by some index. This is the condition for normalizable functions. We have many situations. One of the situations we studied in the last lecture, that is the infinite well or the particle in a box. So one important conclusion that we have reached here till now is that boundary conditions or boundaries give rise to discrete energies. So when we have a bounded system, its energy is quantized. Bounded system has energy in quantized form. Quantized means it is specified by a number, by an index n. This is the significance of the bounded system. On the other hand, we have non-normalizable wave functions, that is the free particle, and that are labeled by a continuous variable k. We don't have n here. The quantization of energy, the quantization condition is not applicable in the case of free particle or non-normalizable wave functions. They do not lead to some physically acceptable states. The physically acceptable state is realized only when we integrate over all the available values of k. The wave functions for the two cases, normalizable and non-normalizable, they are similar in the sense that they are linear combinations. Both follow the linearity condition of Schrodinger equation, Schrodinger theory, and they are different in the sense as the bound states are represented by 1 in the case of summation over n, summation n in the case of bound states, normalizable wave functions, and in the case of non-normalizable or free particle, they are replaced by integration over k. We have seen the situation psi k xt dk. So this is the basic difference. Now let us try to see, because this concept will be very important in discussing the Dirac delta function. Now let us consider a few situations. First we will look into the classical picture. Then we will go to the quantum picture. Suppose this is the classical picture. There is a particle or some object which is fixed or which is moving in a region of potential Vx. We have a potential Vx that is dependent on space, and a particle with energy E necessarily this energy is less than the potential energy. This is the total energy of the particle. Energy E less than Vx is inside this region, is inside the region. So what is happening classically in the classical picture? The particle, this is the particle, this diagram you can get in any book for quantum mechanics. This particle will move in the region of potential, and there are turning points, classical turning points. The particle will come from here, cover this path, go to this point, and then again return. So the particle is trapped inside this region of potential. So in the classical picture, what we have in the classical picture, the particle with its total energy E less than the potential energy of that region will be trapped in the region, will be trapped in the region, similar to that particle in a box, and can never go out, and can never get out. It cannot go out of that region. It will move between the turning points. At the turning points, what is happening? The kinetic energy is changing into potential energy, and again it is taking back to the kinetic energy form. It will be trapped. It is closed inside that potential region. It cannot go out. Similar to a pendulum. Similar to a pendulum. For more simplicity, I am taking this example. I will cite another example. Suppose this is the pendulum. It is going to this max. These are the two turning points, the amplitudes. It is going here, again coming back, again going there, this side, again coming to the center. So it cannot move beyond this. In the small oscillations, we study this thing. The situation is here. You can see a person who is trapped inside this region, and he is running. He is running and continuously running. His energy is less than the potential. Potential means this one. This is the height. So potential is a form of energy. His energy E is less than V naught. This wall does not always mean that it is a wall made of bricks or made of some material. It is a barrier in the form of energy. And this person's energy is less than V naught, and he is continuously running and trying to cross this, and he cannot cross this wall because this energy is much larger, and he goes on running in this region. He will go this side, again turn this side, and go on running in this region. The person is trapped. This is the classical picture. Person is trapped inside the region. Inside the region. This is the classical situation. This happens in the classical situation. So this situation, physically it means it is a bound state. Bound state. The person is in a bound state, or the particle is in a bound state. The particle is in a bound state as it cannot get out of the potential. So it is bounded by the potential. As it cannot move out of the region, and it is bounded by the potential. Bounded by the potential. This is a bound state. For example, you have studied modern physics, and you have seen and you must have studied the Bohr's theory. This is the nucleus, and around these orbits, they are the electrons. These electrons are bound. When this electron gets enough energy, it will get out of that orbit, and it will become a free electron. So this is the classical picture. Now in case suppose the energy of the person or of the particle it exceeds the potential energy at one side or on both sides, then what will happen? That the particle will, this is the situation when E is energy of the person, it is greater than this potential. So it is something like this, that the person is coming through this side, crossing this hill, and then again moving to the other side. So he is not bounded, not bounded. Okay, the particle, what happens to this particle? The particle will approach the region, the potential region from infinity. Some of its energy, some of its energy will be dissipated in overcoming the potential, dissipated in overcoming the potential, sorry, the potential. Then it will escape on the other side again to infinity, and then it will escape, it will escape to the other side to infinity, escape from the other side, similar to crossing a hill, other side to infinity. So what matters here is that how the potential is varying at infinity, how the potential it varies at infinity. This type of situation, this next situation that I have discussed, when the energy of the particle is larger than V naught or the potential in that region, this state is called scattering state. And this is very important when we study the nuclear physics experiments, the scattering cross section and all those theories. So this is the situation that I have described you, and these two situations are very important in classical and in quantum picture. Now where the difference arises, the difference arises in the case of quantum mechanics or the quantum mechanical situation, when the particle energy is less than V naught, the particle can the particle can leak or tunnel out. We will discuss this thing in detail in the later sections. So this is the quantum mechanical picture. This is the barrier. This is the energy of the person. Classically, he could not go out of the situation, go out of this boundary, but quantum mechanically, he is leaking out from this region, from this opening. There is some sort of opening. Imagine that there is some sort of opening, and this leak or tunneling is not allowed in classical physics. Is not allowed in classical physics. Classical physics, when energy is less than V naught, but it is allowed in, it is possible in quantum mechanical situation, and that is called the quantum mechanical tunneling, and it has several interesting applications. We will see what are those applications. So this is the situation that we are observing here. So what matters here, what I want to say, that the solution of the Schrodinger equation, it corresponds or it depends on the bound states and the scattering states. So the only thing that is important here is the variation of the potential at infinity. What happens at large distances? This is important before studying the Dirac delta function. So the important situation is, let me write it in a separate page. So the important situation is important situation is the potential or the variation of potential at infinity. At infinity. So, what are the two states? How you differentiate the two states? The two states correspond to the energy of the particle compared to the potential energy, and it varies as if E is less, total energy of the particle is negative, it is a bound state, and if total energy of the particle is greater than 0, positive, it is a scattering state. It is no longer bound. So these are two important situations. So let us now move to our question, the Dirac delta function or the Dirac delta potential. As I told you, Dirac delta potential is another kind of potential that is encountered in the quantum mechanical situation, and quantum mechanics solution of time independent Schrodinger's equation is all about solving the equation in different situations. So this Dirac delta potential has a shape like this. What happens? What is physically it means? The function has a very narrow spike at some point originally, at the origin, sorry. So the variation, mathematical variation, it is represented by delta. So delta x, it is 0 if x is not equal to 0, and it is infinity at x equal to 0, means at x equal to 0 the potential rises to infinity, and that is why I discussed the previous two situations, the energy, the potential at infinity. So we are dealing with infinity here, and if you start integrating this potential from minus infinity to plus infinity, this function, it comes out to be 1, similar to the normalization condition. Similar to the normalization condition. Let me write it in detail. The potential is such that it is 0. It is 0 at x not equal to 0. The particle is moving in this region, x less than 0, x greater than 0. It is not experiencing any force. Here potential is 0. Suppose this is x equal to 0. I am considering the simple situation. This is x positive x, this is minus x. Here potential is 0, and all of a sudden at x equal to 0, the potential rises to infinity. So Dirac delta function is, let me write it first, rises to infinity. So Dirac delta potential is important. Why it is important? Try to understand, and please watch the full lectures. It is for your benefit. Many people are there who are teaching these things. They are giving the as usual bookish lectures. Don't mind if you are fan of some online teacher. But I try to discuss with you. What is the, if someone asks you, what is the significance of this Dirac delta potential? What is the significance of Dirac delta potential? Dirac delta potential. The significance is, in other examples, like I discussed the particle, free particle, and I discussed the particle in a box or the well. In those situations, the potential was 0. In other situations, the potential may take some finite value. This is the situation where we are dealing with infinity. The potential rises to infinity, it has no limit. This is the case. This is the case where the potential rises to infinity. Rises to infinity. This is the significance of the Dirac delta potential. And thus, we have to check the applicability or the conditions of wave functions. We have studied the conditions of wave functions, well-behaved functions. We have to check them because they should be normalizable. As I told you, they should be normalizable. Means they should be finite, they should be finite, they should be single valued. But here we are dealing with something which is infinity. Then what is the situation? Now let us first discuss a few important properties of this Dirac delta function. Properties of, I am writing DD, Dirac delta function. And one of the most important property is that if you have Dirac delta function, it is denoted by this delta x minus a, then it would be a spike of area 1 at the point A. Is a spike. Spike means something very sharp like this. Is a spike of area unity. That is why the integral is going to 1, it is equal to 1 at A, at x equal to A. So this potential is such that it is picking up the value at x equal to A, and it is not considering any other value. So this is a very strange, very interesting situation. It picks up the value at x equal to A, and everywhere it is 0. It is the situation as if someone is coming in with a clear intention that I will do this thing, I will take this thing, and I will not care about anything. This is a similar situation. So one important thing is that if you have a function fx and then you have del x minus a, it is equal to fa, and it is del x minus a. This is the reason. So this is a significant property of the Dirac delta function, and we should know this thing. Even if you integrate the Dirac delta function with another function fx del x minus a dx, it will be equal to fa, value of the function at x equal to a. It is not picking any value, it is not giving any result at other points, it is only picking up the value of fx at x equal to point A. So now let us come to our potential, come to our situation of Dirac delta function potential. So the Dirac delta potential is of the form Vx. Vx is varying such that it is minus alpha del x. This form of equation you can get in any books. This is a constant. This is a constant. So our potential is such that it is showing a spike at a particular point, and thereafter it is 0. On the left and right of that spike, it is 0. It is a very sharp spike. Area is 1. So let us write the Schrodinger equation for the Dirac with this potential of equation number 1. The form of Schrodinger equation for potential given by 1 is, so it is minus h bar square by 2m d2 psi xt dx square minus alpha delta x psi xt, and it is E psi. So this is the potential, so Schrodinger equation. Now the solution The solution of this equation, before going to the solution, as I told you, you have to take care of two things. Before going to the solution, we have to take care of two situations, and these two situations, they yield physically different results. Two situations that describe two physical situations. What are the two physical situations? We will consider for the first situation where the energy of the particle is less than zero. Now you can ask why we are considering this. Because it is a very narrow spike and there is no, no boundaries. The answer to this question I told you a few minutes back, that here we are interested about the variation of potential to infinity. So what our situation is, we have the x-axis, and on the x-axis at x equal to 0, our potential is, it is minus alpha del x. So you can think of this situation as going down, negative. From this side the particle is coming, this is x equal to 0 and this is x equal to a. If the particle has less energy than the spike at this position, this is Vx, energy is less than Vx, what will happen? Will the particle cross or will the particle stay here? So let us first discuss the situation. In the region x equal to x less than 0, in the negative x-axis where potential is 0. Now this is a free particles case, but you have to remember one thing. Most of the students commit a mistake. You have x less than 0, Vx equal to 0, and you must remember that E is also less than 0. So what is the typical form of solution? Your Schrodinger equation reduces to d2 psi upon dx square, and you take minus 2m by h bar square E psi, and you consider this as k square is minus 2me by h bar square, because energy is negative. This is a very important case. This is a very important consideration when you are trying to solve the problems. Don't take energy is positive. So what will happen? K is minus 2me by h bar. This is of course a complex quantity, and I told you in the previous lectures to always remember this thing, that K is related to 1 by lambda, the de Broglie wavelength. So what does this mean? Does it mean that the wave number is a complex quantity or it is an imaginary quantity? If it is imaginary, then how can a wave number be imaginary? Is it possible? Is it physically acceptable? Well, let us see what is the situation. The general solution is, you could have answered this question if you have studied the electromagnetic theory. So let us discuss here in the most simple form. The general solution as prescribed by your differential equations theory is this kind of a solution. This is perhaps equation number 3. Now what you have to see, you have to evaluate these constants as I told you, and to find A and B, evaluate A and B. we use boundary conditions, and here we have something different from what we have studied till now. Boundary condition. What is the boundary condition? Boundary condition is that if x is minus infinity and you have your psi x, let me write it here also, a e to the power minus kx plus b e to the power kx, at x equal to minus infinity, this term blows up. So at x equal to infinity, let minus infinity, a blows up, and that will not lead to a physically acceptable wave function. So to make the wave function physically acceptable, make the wave function physically acceptable, physically acceptable, we have a equal to 0. So the wave function or the solution of the time independent Schrodinger equation for this solution becomes b e to the power minus kx. So it is a negative exponential solution. This is perhaps equation number 5. So in the negative x side, what we have? We have a negative exponential. Negative exponential means exponentially decreasing. Analyze the situations with the knowledge that you have in the most simple manner. This is exponentially decreasing. Means, what does it mean? At x equal to 0, you have this spike. This is x negative. This is positive. Here, the wave function will be decreasing exponentially. Means the probability of finding the particle which is related to this, it will also decrease. This is the first clue that we are getting. It is not the complete answer. Now let us check the solution in the region of positive x. Now we have in the second region x greater than 0. What happens in x greater than 0? We will get similar kind of a solution. Again at x greater than 0, remember Vx is 0 and energy of the particle is less than Vx. Then the general solution will be something like that: f e to the power minus kx sub psi x a plus g e to the power kx. So x at x equal to plus infinity, this g factor, you must have heard this word. The second term will go to 0 as x tends to plus infinity. So what your solution at x greater than 0 is x f e to the power kx minus kx. Now what we have been, now concentrate, wait for a while, I am stopping writing. Now what you have done in previous cases, in potential well, in harmonic oscillator, I will discuss these things in your what is called the infinite well. What we do, we match the solutions, at x negative and x positive at the point of discontinuity, x equal to 0. So what is happening? X equal to 0 is a point of discontinuity. There is a spike. Here you have the wave. Here you have the wave. You have to match these two. You have to connect these two. How do you connect this? We use the conditions for well-behaved wave functions. Well-behaved wave functions. This is the condition we use. But wait a while. What are the wave conditions for well-behaved wave functions? The conditions for well-behaved wave functions are: 1. Psi must be continuous. continuous at x equal to 0, which is the point of discontinuity, of course, in this case, and d psi by dx must also be continuous. Must also be continuous. So if we apply the first condition at x equal to 0, we have psi x is b e to the power kx at x less than 0, and it is f e to the power minus kx at x greater than 0. Then at x, put x equal to 0, what you get? F equal to b. This is equation number 6. Now we are worried about, I should say we are worried about the boundary conditions, that is in the second case, that is the second condition. I am worried about this condition. To understand this situation, this is the condition that is worrying me. What will be the solution? The second boundary condition, that the derivatives must be continuous, it will not lead to any physically acceptable condition. And what we have done till now, it is the same thing that we have done in the other cases, in the previous potentials. So how can we apply the second boundary condition, the continuity of the derivatives? That will be the most important thing. And we will discuss this thing in the next lecture. And then you will understand the significance of the Dirac delta potential. So the PDF link will be provided in the WhatsApp group. The description will contain the Telegram and WhatsApp group links. You can join, and please watch, like and subscribe the videos. That will help you more than me. Thank you.